Hi, welcome to my talk, We've Got Real-Time Networking at Home, Why Many Systems Are Moving to TSN So Slowly. My name is Johannes Zink. I'm a kernel developer at Pangotronics, a Linux consulting and kernel development company located in Hildesheim in northern Germany. Before I began my work in the Pangotronics kernel team, I worked for roughly 10 years as a systems engineer and network engineer, mostly dealing with different legacy and modern implementations for real-time networking. In this talk, we will discuss examples for applications using real-time networks. We will look at the specific requirements for these applications and how legacy implementations tried to implement these requirements. After comparing these implementations to TSN, time-sensitive networking, I will suggest how to migrate already deployed installments towards TSN. And last but not least, we will have a look on the role of Linux networking and discuss what future developments may become relevant in this area. To start things off, let's have a look in some examples for applications benefiting from real-time networking. One example we will look at in more depth is machine control. Think about a large manufacturing plant where multiple stations along a production line have to interact and work together to manufacture a good. Many different drives connected to a central or sometimes even to multiple decentralized programmable logic controls and having to perform tightly coupled coordinated movements. Control loops read values measured in the physical world at input nodes, process them and set output values accordingly and in a timely manner. These systems are usually carefully and precisely engineered and thoroughly tested. Since failure to process data coming into the system in time may lead to damaged goods, damages in the production plant, or may even cause severe injuries to persons who operate and interact with the production line. It is therefore absolutely crucial to make sure that the control data flow is not disturbed in any way. Another example we will look at is audio-video bridging. Imagine a large concert where a band plays on stage, audio data is pre-amplified and converted into digital signals in so-called stage boxes and sent back to a digital mixing desk in the back of the venue called the front of house, where a balancing engineer will adjust the sound and again use the network to send it back to the front of the venue, where power amplifiers will amplify the signal and drive the loudspeakers and make the result of this entire chain heard to the public. Nowadays, of course, video is collected from multiple cameras and sent to a vision mixer and played out, for example, to video vaults accordingly. These setups tend to be set up much more in an ad hoc fashion, in contrast to the pre-calculated and pre-engineered machine control networks. However, these live video and audio setups require low overall latencies, where the network packets containing the samples need to be delivered in time and very reliably. Failure to do so will lead to very audible dropouts or distortions. The sampling clocks used for analog to digital conversion and vice versa need to be synchronized very precisely. Otherwise, noise and unwanted audible artifacts will appear in the audio signal. Also, it should be noted that these setups usually require protection against failure of the transmission links, because especially optical links can fail under the harsh environments found in backstage environments. Other applications include aerospace or automotive applications, amongst many others, but we will not look into these today. One requirement all these applications have in common is a common notion of time across the different entities connected to the network. Any device in the network has an internal clock, which is usually using a crystal oscillator connected to a counter, registering the oscillator cycle since the oscillator started working. Because the different entities are not powered on at the same time, the oscillators do not start counting the cycles at the same point in time. In addition, due to manufacturing tolerances, temperature drift and many other effects, oscillators have tolerances with respect to their nominal frequency. This issue can, however, be addressed quite similarly to old-fashioned movies, where amongst multiple clocks the best one is selected and other clocks are corrected for minimal error to this reference clock. Now that we have established a common sense of time passing throughout the network, we can easily synchronize actions, sampling clocks, or even network packet transmission times across the entire network. Another important requirement is a bounded transmission latency for a defined path in the network. When a network packet passes through so-called bridges, which is a term used in the standards for switches or routers, the packet is buffered in an input or ingress queue. Then the bridge decides where the packet needs to be sent, and the packet passes through the output or egress queue to the output port. Since the bridge output may already be sending another packet and therefore be occupied, while at the input another packet for the same destination arrives, queuing is required. Since the network link, of course, can only carry a single packet at a time. Across a packet's path through the network, this queuing adds a little delay for each bridge the packet passes by. This amount of time is called the residence time and accumulates over the path through the network. Since real-time applications require packets to be delivered within a certain time frame, this is problematic as soon as the interfering traffic occurs at a bridge. If now the path is blocked due to other packets in flight, the packet from the left source, or talker as the standard calls it, may not reach the sink or listener in time anymore. This is to be avoided under any circumstances, since failure to deliver packets within the predefined time frame violates real-time guarantees of the system. The most common way to solve this issue is to introduce means of giving the real-time traffic priority over the remaining traffic. I've chosen this picture because it shows a real-world application of this approach. Since the bus has to reach real-time requirements, that is basically keeping a schedule, and might be impeded by interfering traffic, a bus line has been introduced to give it priority over all the remaining traffic. As long as everyone respects the rules, this will work reasonably well both in the real world and in networks. As an example for additional and often application-specific requirements, I choose physical layer redundancy, or link redundancy as it's called sometimes. This feature is very important for at least some applications. If you remember the example I gave for audio-video bridging, how annoying would it be to trip over a network cable and just tear down or end an entire large live concert? But also other applications such as industrial manufacturing plants may benefit from this feature, for example, for replacing faulty wiring without having to shut down the entire network plant. Now that we have collected the most important requirements for real-time networks, let's look into how legacy implementation approaches look like. For the first important component, time synchronization, most implementations use PTP or similar implementations. PTP is short for Precision Time Protocol, which is standardized in IEEE 1588. Nevertheless, over the years I have encountered variants or completely divergent implementations, which often cannot benefit from hardware offloading support in modern chips. Bounded transmission latency can, in general, not be guaranteed in legacy implementations. For some applications relying on best effort, which is basically hoping that packet delivery is good enough in most cases, increasing buffer sizes to account for interfering traffic and such is a common practice, especially seen on converged networks. For some applications, pre-calculation of required bandwidth and timing margins and carefully designing network structures and link speeds has worked reasonably well in the past. This can, of course, get supported by taking measures for improving quality of service for the real-time traffic. Either entirely segregating real-time traffic from non-real-time traffic by simply using separate physical links, or employing prioritization measures like DSCP. The overall system behavior can often be improved against unconfigured networks. This requires, however, deep knowledge of networking infrastructure, protocols, and gear configuration. Also, it will usually not provide any guarantees. When using such network setups, you are, in the end, left hoping that anything will work out well. TSN in turn provides, in the meantime, a quite large set of standards, fixing all the issues we discussed so far. TSN has defined a subprofile in the precision time protocol called GPTP, Generalized Precision Time Protocol, which basically improves the precision even beyond what is possible with conventional PTP. Traffic shaping basically is the most extreme possible implementation of quality of service one can imagine. Before sending real-time data or real-time traffic on the network, the bandwidth required for this data has to be reserved. This bandwidth is exclusively reserved for this data stream and is guaranteed to be available within every observation interval. This means that within the observation interval, that is a 2 or 4 millisecond time frame, depending on the traffic class, a part of this time is exclusively reserved for sending prioritized data. No interfering traffic is allowed to be sent in that time. The remaining time and bandwidth is shared amongst all remaining unprioritized traffic. Overcommitting bandwidth on real-time relevant data streams is no longer possible with this attempt, which ensures that enough bandwidth is available to carry each established stream across a data flow path. If no more bandwidth is available, the stream cannot be established. For a seamless transit of frames throughout the network without long residence delays, this requires all bridges to be time synchronized, which is implemented via GPTP, as we already saw. Setting up streams and asserting whether bandwidth is still available or not on different routes requires communication between the different endpoints and bridges. The TSN standard set defines different possible protocols for reserving individual streams dynamically or setting up an entire network at once. This covers all relevant use cases from entirely dynamic setups with devices being plugged to and removed from the network to entirely static setups, which may benefit from having the possibility to pre-calculate required bandwidths along different links and along different flow paths. Basic physical link layer redundancy is already solved with the PCR, that is path control for reservation, and FRER, frame replication and duplicate elimination for redundancy, though these have only limited support for more complex redundancy schemes. Some aspects relevant to at least some applications are not covered by TSN, for example routing, since TSN is a set of layer 2 protocols, whereas routing requires a layer 3 on top. Now that we discussed the advantages of TSN for real-time applications, let's have a look on how to upgrade installations already deployed in the field, so-called brownfield appliances. The devices deployed in the field are usually not capable of simply replacing legacy networking solutions to TSN by just upgrading the device firmware. This is due to TSN requiring hardware offloading for several of the main features it offers, such as GPTP or traffic shaping. Even if a part of the devices in the field can be replaced by a TSN-ready hardware, usually the system itself, meaning the entire system, cannot converge with TSN, since TSN requires all devices taking part to comply with the standards. For example, every device has to implement GPTP, even the switches involved, otherwise no bandwidth reservations can be established, since no common time base can be distributed over GPTP. An entire system is, most of the time, not possible to be upgraded, since it would basically require to replace all networked endpoints and bridges relevant to real-time traffic, which is often simply too expensive. Instead, upgrading single subsystems has shown to offer real advantages at moderate costs. This allows, for example, to replace all components across the most critical links and establishing TSN communication at least for the most critical components. Existing legacy field buses or legacy Ethernet installations can be interfaced via gateways without interfering with the TSN traffic on the subsystem's backbone connection. By using TSN-capable hardware for replacements, extensions, or future installments, these TSN insulars can be gradually expanded. This allows larger and larger hunks of the installation to use TSN internally until eventually all devices are migrated and TSN can be used throughout. Now that we know of the benefits of TSN over legacy implementations and have roughly sketched an approach on how to deploy it, let's discuss the role of Linux networking and the Linux community in this. First of all necessary standards and components are already supported in mainline Linux. This is absolutely amazing, especially for an open source system that anyone just can use. Some of the later extensions, for example for PCR, for offloading, have prototype implementations are currently worked on, but will very likely make it into mainline very soon. Linux is an excellent basis for development due to the overall high-quality implementation of the network stack, since even hardware offloading for most TSN-related topics is available. High-performance real-world implementations can already by now be prototyped very quickly. Nevertheless, the community will, in general, still need to improve on the user space API, the documentation. At the moment, configuring a Linux system to interact properly and standard conformant with other TSN systems still requires some effort and knowledge about the standards involved. Also, adjusting the right knobs still requires some manual tweaking, since daemons and services for configuration are not yet available for all possible modes of operation that TSN offers. Some implementations for singular tasks exist, but still require some work to properly work together. Also, finding the proper settings for some of the components is still to be improved upon. Choosing and documenting good default settings can improve the situation a lot, and some developers already have demonstrated that. Especially hardware and board vendors, but also project leads for TSN-related projects may find that providing examples and reference designs will help to push technology in the field a lot. This especially helps engineers new to this field to get setups up and running quite fast and adapt them to their needs. Last but not least, there is only a few open source test and validation tools for TSN available. Having more of them available would make a huge change and also help to get TSN out to the world much faster. Because of the always evolving nature of the Linux kernel, upcoming new developments to real-time networks such as DetNet, an effort at the Deterministic Networking Working Group at the IETF to extend TSN up to OSI Layer 3, basically making it routable, hence the name, will very likely be included as they are evolving. As I already pointed out, standards are evolving and remaining issues need to be addressed. While some of the feature gaps will be filled by DetNet, some of the existing higher-level application protocols are not very well suited for being transported over TSN. We will, as a community, probably see better fitted protocols evolving over time, which make better use of the real-time guarantees made by TSN and fit better into the overall design. For easier and broader use of real-time networks, user interface design and providing good default settings to make devices work well out of the box will be needed. Especially integrators and the end users play a crucial role in rolling out real-time networking into real production systems. Providing configuration and usage examples gives a good point for getting started, especially to new end users. While good reference designs will help the integrators in turn to build new devices upon this technology. Last but not least, at the moment it is still hard to verify whether a system works as intended, and debugging is sometimes even harder. Access to good and open debugging and validation tools will help to spread TSN a lot. This brings me to the end of my presentation. Thank you for your attention. If you are interested in implementing a TSN system with Linux, improving documentation, tooling, or want to discuss on protocol and interface design, please do not hesitate to write me an email at j.zink@pangotronics.de. That's j.zink@pangotronics.de. Thank you for your attention. See you soon.